Hello chemistry students, Dr. Tullis here. This chapter is about solutions and their behavior, and we're going to work through it together. In our first section, we're focusing on what a solution is. It's a homogeneous mixture of two or more substances in a single phase. For example, air, gasoline, a soft drink in an unopened container. And a solution is composed of a solute and a solvent. A solute is the substance that is being dissolved. It's the minor component. The solvent is the substance that's doing the dissolving. It's the major component. Water is a very common solvent that's used in most Gen Chem applications. This chapter focuses on the properties of solutions. Experience tells us that adding a solute to a pure liquid will change the properties of that liquid. That is the reason some solutions are made. For instance, when we add antifreeze to the water in your car's radiator, it prevents the coolant from boiling in the summer and freezing in the winter. Freezing and boiling point, osmotic pressure, and changes in solvent vapor pressure for solutions are examples of properties that are discussed in this chapter. Those are called colligative properties. The properties of a solution that depend only on the number of solute particles per solvent molecule and not on the nature of the solute or solvent. Some different quantitative calculations that we'll be doing, we'll be measuring weight percent, parts per million, parts per billion, mole fractions, molarity, and molality. Let's look at molarity first. This should be review from previous chapters. Molarity is moles of solute per liters of solution. It's denoted with a capital M. Again, it's moles per liter. What's the molarity of this solution? If I have 0.175 grams of ammonium acetate dissolved in water to make 45 milliliters of solution. First, we need to convert grams to moles. Because again, molarity, we have to get moles on top and we need liters on the bottom. So we need to write out ammonium acetate. We would find its molar mass and we would have 0.00228 moles of ammonium acetate, and 45 milliliters is the same as 0.045 liters. So our molarity would be 0.051 molarity. Another quantitative aspect of solutions is finding the molality. Notice the difference in spelling. Molality is moles of solute per kilograms of solvent. So not moles per liter, this is moles per kilogram. To prepare a 1 molal solution, so to have 1 here, we would need 1 mole of solute added to 1 kilogram of solvent, in this case, water. We will also be calculating mole fractions. The mole fraction, denoted X, of a solution component is defined as the amount of that component, so the amount in moles, divided by the total amount of all the components in the mixture. So if I was given grams of, let's say, ethanol, and it was dissolved in water, let's say 162 grams of water, I need to get grams of ethanol into moles of ethanol. That would be 1 mole of ethanol. And then my grams of water into moles of water, and add up that total amount of the ethanol and the water. So the total solution would be my denominator. If I want the mole fraction of ethanol, I take the moles of ethanol divided by total. And if I want the mole fraction of water, I take the moles of water divided by the total for the solution. Notice that both of the mole fractions, whether there's only just 2 components or maybe there's 3 components, maybe there's 4 components, but all of them added together should equal 1. Another quantitative aspect is weight percent. To find weight percent, similar to the mole fraction, we just take the mass of A divided by the total mass of the solution and times it by 100. So instead of just doing the moles of A divided by total moles, we're taking mass divided by total mass. Let's say that alcohol water mixture from before, we take that 46.1 grams of ethanol. To find the weight percent of ethanol, we would use the ethanol as the numerator. And then I add together the ethanol and the water would be my denominator. Times it by 100 to get a percent. Again, this is weight percent. Let's look at an example. Suppose you add 1.2 kilograms of ethylene glycol as an antifreeze to 4 kilograms of water. What are the mole fractions, the molality, and the weight percent of the ethylene glycol? I took my grams of ethylene glycol and went to moles of ethylene glycol because I wanted to start with my mole fraction. But remember, if I have this as my numerator, my denominator needs to be both of the components in this mixture, in this solution, as my denominator added together. I have 4 kilograms of water, which is 4,000 grams. So I went grams to moles. That's my moles of water. Let's add both of those up to find my mole fraction of glycol. I'm going to take my moles of glycol divided by moles of both of them added together, and I got 0.080. To find the molality, remember, is moles divided by kilograms. So to find that for glycol, I took the moles of glycol divided by kilograms of water. I got 4.8 little m, or you can say 4.8 moles per kilogram. And the weight percent of glycol, again, I want to take the mass. 1200 is 1.2 kilograms. That's for glycol. And I'm going to add my glycol and water in the same unit and times it by 100, 23%. Pause the video here and try to do this sample problem. Let's see how you did. I had 10 grams of sugar. I went to moles of sugar, finding the molar mass of sucrose. I had grams of water. I went to moles of water. And we're finding here the mole fraction, the molality, and the weight percent of sugar. So sugar is going to be my numerator in each of these. So to find the x of sucrose or sugar, there's my moles of sugar divided by total moles to get this answer. My molality, my moles of sucrose or sugar over kilograms of solvent to get that. And the weight percent is grams of sugar or sucrose over total grams to get 3.85%. Our next quantitative measurement is parts per million, ppm. ppm, we take the mass of our solute divided by the mass of our solution and times it by a million. The units parts per million also refers to the relative quantities of solute and solvent by mass. 1 parts per million represents that I have 1 gram of a substance in a sample with a total mass of 1 million grams, which is equivalent to 1 milligram or 0.001 grams in 1,000 grams. The parts per million is typically used to identify concentrations of solutes in very dilute solutions. It's useful in chemistry, especially in environmental chemistry, in disciplines such as biology, geology, and oceanography. Here's an example. If I had 5 grams of salt dissolved in 500 milliliters of water, we would do 5 divided by 500. We know 500 milliliters is equal to 500 grams, and that would give me 0.01. Then we times it by a million, and that would tell us that we would have a concentration of 10,000 parts per million. I have 5 join-in questions. Pause the video here. Check your answer. Pause the video here. Check your answer. Pause the video. Check your answer. Pause here. Check your answer. And the last one for this section. And check your answer. That completes section 1.